periodic table is comprised of metals, which are most of the elements, nonmetals, and metalloids. Metals typically have a shiny luster. They can be different colors, but many of them are silver. Solid metals are malleable, meaning they can be hammered and shaped. They're also ductile. They can be drawn into wire. And they're good conductors of heat and electricity. Mercury exists as a liquid, but cesium and gallium both melt just above room temperature. That's gallium. I wouldn't advise putting cesium in your hand. The more an element exhibits these properties, the greater its metallic character. And metallic character increases as you move down a group and as you move from right to left across a period. Remember that metals have lower ionization energies, and so they form positive ions or cations fairly easily. Cations form when electrons are lost, and loss of electrons is oxidation. And so metals are oxidized in chemical reactions. When metals are bonded to nonmetals, the compounds tend to be ionic because of the complete transfer of electrons. And when the metal is bonded to the nonmetal oxygen, it's known as a metal oxide, most of which are ionic solids and are basic because the oxide ion reacts with the water to form hydroxide ions. Metal oxides, for example, nickel 2 oxide, are also basic when reacting with acids. And of course you remember that a base plus an acid produces a salt and water. Nonmetals can be a variety of colors, like phosphorus, sulfur, and carbon. And 7 of the nonmetals exist as diatomic molecules. We call them the super 7 because they make a 7. If you start with number 7, then you got to remember about hydrogen over there. Bromine exists as a liquid. Iodine's a very reactive solid, but the rest of them are gases. Nonmetals tend to gain electrons when they react with metals because they have a high electron affinity. And when the nonmetal gains an electron from the metal forms a positive cation, the nonmetal forms a negative anion. The opposite charges attract, electrostatic attractions pull them together, forming an ionic bond from that complete transfer of electrons. But when nonmetals bond to other nonmetals, for example, here, carbon and oxygen, they form molecular substances with covalent bonds. And so the electrons then are shared rather than transferred. Most nonmetal oxides are acidic. Sulfur trioxide is a molecular compound. It's a nonmetal oxide. And it's a byproduct of some manufacturing processes. And so it reacts with water vapor to form sulfuric acid. And that's one way that acid rain is formed. Nitrous oxide is another byproduct of manufacturing as well as emissions from petroleum products, and that's another way that acid rain is formed. And like acids, nonmetal oxides react with bases to form a salt and water. Metalloids on the periodic table are between the metals and the nonmetals, so it stands to reason that their properties are going to be also somewhere in between. And the most notable of all of the metalloids is silicon. Its properties as a semiconductor make it an excellent substance for use in computer chips and processors. Let's take a look at the group 1 alkali metals in a little bit more detail. Like sodium here, they're soft metals, silvery, with a luster, and they're excellent thermal and electrical conductors. Sodium and potassium are both group 1 alkali metals that are necessary for our physiology. Remember the sodium and potassium pump? Both of those ions are going to be moving in opposite directions across the plasma membrane. It's important for the functioning of nerve cells and maintaining cell volume and in active transport. We know that looking down a group on the periodic table, atomic radius increases. So does reactivity. Sodium has one valence electron, just like cesium does. But since cesium is so much larger, and its valence electron is so much further from the nucleus than sodium's valence electron would be, and cesium experiences so much more shielding from the attraction of the protons in the nucleus due to its size, and that gives cesium a really low ionization energy. That means that valence electron can be removed very easily, making cesium very reactive. Because these alkali metals are so reactive, you won't find them in their pure forms in nature. They'll only exist in compounds where they're nice and stable, mostly bonded to nonmetals. Sodium, so reactive with water, you wouldn't want to just throw it by itself into your soup. And chlorine is a toxic gas. Yet when sodium bonds to chlorine, we get sodium chloride, which is pretty harmless unless you have high blood pressure. When a group 1 alkali metal bonds with hydrogen, they form metal hydrides and sulfur to form sulfides. And of course we know they're very reactive in water and water vapor, and so they're usually stored in mineral oil or kerosene. The group 1 metals will also emit distinct colors in a flame test. And as we go down the group, we can see that lithium is a red color, sodium is yellow, and potassium is a violet, going from a low energy color to a higher energy color to a still higher energy color. In a flame test, we energize the salt with the flame, and what that does is it excites the valence electrons to move into higher energy levels. And then as the electrons move back into their ground state, they emit that energy that was absorbed in the form of photons of light. And the greater the N value for an element, or the larger size atom of the element, the more electrons, the more shells it's going to have available for those excited electrons to move out to. And so if those electrons can move out even further and absorb even more energy, when they move back into their ground state, then that greater absorbed energy, that greater amount of energy, is going to be emitted as a higher energy color. That's why we have sodium, potassium being the largest of the three, emitting the highest energy color flame. Potassium has more energy levels, more shells of electrons, where the excited electrons can move out away from the nucleus to go. Also in group 1, we have hydrogen. It's in group 1 on the periodic table because it has one valence electron. But hydrogen's a nonmetal and it's a gas, so it really doesn't belong anywhere. And hydrogen's one of the 7 diatomics, so it exists normally as H2. Hydrogen gas. But under extreme pressure, hydrogen can have metallic properties. And because of its small size and lack of shielding, although it does give up an electron, it doesn't do so as easily as the alkali metals would. It's got a slightly higher ionization energy. And don't forget that hydrogen can also gain an electron when bonded to a metal, as in sodium hydride. So look at all the things that hydrogen can do. It can lose an electron and form hydrogen ions. It can gain electrons and form hydride ions. And it can share its electron and bond covalently, like with water. Let's take a look at the oxygen family now. Oxygen's the only gas in the group. Oxygen, sulfur, and selenium are nonmetal, but when you move down the group, metallic character starts to increase, and tellurium is actually considered a metalloid. And polonium is rare and very radioactive. Oxygen's usually diatomic, but it also has an allotrope, O3 or ozone, which is produced by lightning and is kind of smelly. Below oxygen we have sulfur, which has a few allotropic forms, but the most common is S8. And sulfur has a lower electron affinity than oxygen, so it doesn't bond as easily as oxygen does. In group 7, we have the halogens, and they're all nonmetals. And as you look down the group, the more mass of the atom, the higher the boiling point and melting points will be. This is something we'll explore a little bit later on. Fluorine and chlorine are yellowish gases at room temperature. And bromine is a reddish-brown liquid, which vaporizes easily, and iodine is a solid, but it forms a violet vapor very easily. And fluorine, chlorine, bromine, and iodine are all diatomics. Halogens, having 7 valence electrons, have very negative electron affinities. They'll remove the electrons they need to complete their valence very easily, and usually very exothermically. And lastly, we have the noble gases. They're all nonmetals, and they're all monoatomic. And they all have full valences, making them really unreactive. Although some, krypton and xenon, have been forced to react against their will in the chemistry lab.